Okay, we're going to continue working on these graphs in this lecture. Okay, so applications of network theory, many involve traveling around the graph in the sense of moving from node to node along incident edges. So a walk in G is a sequence of edges. Now what I might do here, we won't worry about loops, and let's say remember an edge, if it's not a loop, is a two-element subset of V. So say V consists of vertices V1, V2 up to Vn, so many of them. And so the edges consist of things like, well actually they're subsets, so Vi, Vj, in the set of edges. So an edge between vertex I and vertex j. So for example, if we were to draw that, so vertex I, vertex j, this two element set Vi, Vj would represent this edge. Okay, so how do we write down a sequence of edges? I'm going to write down some kind of symbols like this. Okay, it's kind of actually difficult to do this. I think we'd be better off doing it with an example. Okay, so let's do it with an example to explain these. So these will be, for example. Okay, so let's take four nodes, V1, V2, V3, V4, and suppose the edges something like this. And maybe in this sense we will be able to do a loop. Okay, so V1, V2, V3, V4. Now we can write down the names of the edges now. So this is the edge V2, V3, and you can write the second containing V3, V2, it's the same thing. If it's a loop, it's a single element, V3. And I'm actually going to name these as edges, we'll do that in a second. See, what I want to show is that you can write down the edges, but there's kind of an easier way of doing it, and I don't want to make it really difficult by writing down the edges like this. We're going to call this edge whatever. Let's see. Okay, so this is V2, V4. Order doesn't matter, so let's write V4, V2. This one is V1, V2. And this one here is V1, V4. Okay, so let's call this edge 1, edge 2, edge 3, edge 4, and edge 5. So if you want, you can write a walk as a series of edges. So suppose we go 1, 2, 3, loop, 2, 4. So it's 1, 2, 3, loop, 2, 4. So you could write that as, so you go from V1 to V2, so that's edge 4. Then you go to 3 using edge 2. Then you loop, which is edge 1. Then you go back to 2, which is edge 2. And then finally go to 4, which is edge 3. So you can write it as a sequence of edges, but it's easier to write it like this. V1 to V2 to V3, looping to V3, so V3 to V3, back to V2, and finally on to V4. So this is a sequence of edges, and this is a easier way of writing it. Okay. In walk in which all the edges are distinct is a trail. So for example, if we went, this isn't a trail because it uses edge 2 twice. So for example, if we call this, we'll call this walk 1. For example, this walk, so this is V1 to V2 to V3 to loop, that uses that edge twice, so it's not a trail. So walk 1 is not a trail because you use the same edge twice. Now let's make up something that is a trail. Let's say V3 to V2 to V4. V3 to V2 to V4. It's certainly a walk because it's a sequence of edges, only 2 edges. It's not repeated. This is a trail. Okay. A trail in which all the nodes are distinct is a path. Path, therefore, is a walk in which, alright, so we'll see an example of this in the next page. So now I'm not too concerned about all the main ones we're actually going to be interested here is trail. Path is something that we're not examining because there's only 10 weeks. Although actually it comes into a cycle, so maybe we will include it. So a path is a trail in which all the nodes, now a trail already has all the edges distinct, and if the nodes are also distinct, that's a path. A path, therefore, is a walk in which neither edges nor nodes are repeated, except for perhaps the first node. So we'll do a non-path and then a path. So now I won't, I'll have to label them. So let's say 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and we'll do some. We'll draw some edges in a moment, and then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So let's draw some edges. Usually we're not going to bother with loops, to be honest, in undirected graphs, but they could happen. Okay, so that's okay. Something that's not. So a walk is just a sequence of these. A trail might be 5, 3, 2, 4, 5, 2. So let's write that down. So is that 2, 2, 3, 5, 4, 2, 5? Was it 2 to 3 to 5 to 4 to 2 and back to 5. So it is a trail because it doesn't use any edge twice. Like if we count it, that edge is used, 3 to 5, that edge is used, 5 to 4, that edge is used, 4 to 2, that edge is used, 2 to 5. So it is a trail, yes. I'm just going to write T for trail, yes. Is it a path? No, because the node 2 is repeated. So if we're talking in terms of nodes, now you can finish at 2, that's okay. So 2, 3, 5, 4, 2, and I'm not finished. So this is not a path. Okay, so that's the difference between so a path is a trail. And I think if you think about it, if I'm trying to say, is it possible that you repeat a node and not an edge? Or no, sorry, if you repeat an edge, you automatically repeat a node. So it's not possible to, like, if you think about it, so if you go over this edge twice, unless you go, I think just 2, yeah, actually no matter how you do it, you're going to, if you repeat an edge, you're definitely not, you're definitely going to repeat a node. Okay, let's draw something here. So just throwing in some random edges, and let's get a path. Let's go 1, 6, 5, 3, 4. 1 to 6 to 5 to 3 to 4. So now this is definitely a trail because I don't use any edge twice. I use that once, that once, that once, and that once. So it is a trail. And it's also a path because I don't repeat. See here I had 2 and 2. Here that doesn't happen. These are all distinct. Now if I wanted, I could, I think even if you go back to 5, it's not a path anymore. I'd have to go back to 1. So you could go on to 2 to 1 if you wanted, and it would still be a path. So we'll just write that down here. So we did 1, 6, 5, 3, 4. If you want to go on to 2 and then to 1, that's, even though 1 appears twice, because it's the start and the end, it's okay. So if you add on that extra bit, that's still a path. Okay. A path in which the initial and final nodes are equal is a cycle. So for example, this is a cycle. It's still a path, because no edge or no node is repeated apart from the start and end. So maybe we'll we'll just draw a new graph. Something we'll write. Yeah, we'll just do a new graph. A B C D E F. A B C D E F, and let's do some edges. Now I'm picking these edges randomly. Like, now you can't do that because you'll be given a graph to work with, but okay. So a cycle would be, say, A D B C E A. Cool. So what did we say there? A to B to D to C to E, and if you go back to A, that's a cycle. Now let's go through it all. It's a trail because it only uses A to B to D. It doesn't use any edge twice. C to E, E to A. So it's definitely a trail. It's a path because apart from the first and last, it doesn't repeat anything. And in fact, it's a cycle because it starts and ends. And this green one up here is also a cycle. Okay. Now this one actually uses all the nodes, but to be a cycle, you don't have to do that. You just have to be a closed. So another word for a cycle might be a circle. That'd be another possibility. Now this question is just for one of the learning tasks. So it says two graphs are isomorphic, literally same shape. So iso means same, morphic means shape. If there's a bijection, now unfortunately you don't have the language here of bijection because the questions are out of order. But bijection just means that you can pair up the vertices, basically. Yeah, I can't really use this language, unfortunately. But what I can say is, if you can relabel the nodes, then that they're actually the same graph. So for example, if I draw this and this, so now the labels, let's say 1, 2, 3, 4, 5, A, B, C, D, E. Now it's actually quite a difficult problem to say that two graphs are isomorphic. There was a big breakthrough in this problem, it's a maths problem, relatively recently. The question is how difficult it is to do. So given two graphs, how long does it take to figure out if they're isomorphic or not? And it can be easy to see if things are not isomorphic. For example, if there's nodes of different, like say if this graph has a node of degree 5 and this doesn't, then they can't be isomorphic. So these graphs look very different, but actually they're the same. So the pairing would be if you relabel 1 to C, and then 2 to A, 3 to B, 5 to E, and 4 to D. And there's a few other ways of doing it. The fact that there's multiple ways it captures the symmetry this time. You might say, no, they're still different, but actually if you write down the nodes and the edges, you'll see they're exactly the same, just apart from relabeling. Now maybe we'll try it. We'll maybe write down what we'll do is we'll write down the vertex set and the edge set here, and then kind of compare. So here, the vertex set is A, B, C, D. And the edge set is, what have we got? AB, BE, ED, DA, AC, BC, EC, and CD. So what we're saying is we're just going to show that kind of if we do the relabeling, every single edge is here, and I'll just tick them off. So the A, B, C, D, E is 2, 3, 1, 4, 5, and now the edges. So A to B, there should be an edge from A to B, which for us is 2 to 3, yes. B to E, yes. E to D, yes. D to A, yes. A to C, yes. B to C, yes. E to C, yes. And C to D, yes. And you can see we've captured every single edge. To see that they're actually different, the easiest thing is just to move this 1 into the middle, and then it's the same. So really this idea, I don't think it's going to be examinable. It's just something for us to do a difficult problem, which, okay, as just a bit of a learning exercise. So now next thing, a tree. So a tree is a connected simple graph. Now simple means no loops with no cycles. So let's draw some trees. And we'll draw 3 different trees. So how about we'll draw 4. That's a tree. It's connected. There's no loops and there's no cycles. That's a tree. It's connected. There's no loops, there's no cycles. That's a tree. It's connected. There's no loops and there's no cycles. If I join these up, I get a cycle. Remember, a cycle is a circle, and therefore it wouldn't be a tree. And then a more complicated one. Something like that. So notice that it has no loops and there's no cycle. You can't make a circle in there. And there's always going to be one less edge than the number of nodes. So for example here, number of edges is equal to 0, number of nodes is equal to 1. Here number of nodes is 2, 1, 2, and number of edges is 1. Here number of nodes is 3, number of nodes is 3, number of vertices is 3, edges 1, 2. And here the number of vertices is a bit more, 1, 2, 3, 4, 5, 6, 7, 8. Now let's count the edges. 1, 2, 3, 4, 5, 6, 7. Okay. An example is a family tree. Now how well will this work? I'm not so sure. Like if you just draw any old family tree, will it work? I'm not so sure. I think what we have to do is we have to combine people who are married into a single node. So for example, thinking of my own one, node, I've got a good few brothers and sisters. There's my parents. Then we have, say, for example, my father's parents, mother's parents, then aunts and uncles on my mother's side. I won't try everyone here. Aunts and uncles on my father's side, and then some of them have children, something like that. So in my idea, this is my paternal grandparents, maternal grandparents. Here's some children. Here's some children. Here's my parents, parents of me, and also my siblings. And here's me and my wife and I and our little baby. So a family tree is a tree. There's no cycles in this, and it's connected. Now if you have multiple family trees where people aren't related, then it won't be a tree because it will be disconnected. And here's a good question for you. Suppose we all go up on the board, which we can't do obviously, and draw our family trees, maybe just a little bit back. So what happened now? Some of us will have, maybe some of us in the class are related. We'll just do our parents and siblings, parents and siblings. So imagine we all go up and we all do this. Some of us, so for example, something like this. Now I appreciate this can be complicated, like in fact mine's a bit more complicated because my brothers and sisters are half brothers and sisters. And it could be more complicated. So this is an unconnected graph. So I'm saying this is a one graph. One graph. And each of the components are trees. What do you call this? If you want to pause the video and have a think, the answer is a forest. So an unconnected graph whose components are trees we call a forest. Right. So now I think, what are we going to do? Now there's just some information here, further remark about where does trees and forests come into computer science. There's some stuff here, there's something called random forest. I think we're going to try and look at, so this is normally a collaborative task. So where Tn is the number of non-isomorphic trees with n nodes, find how many trees with one node, how many with two, how many with three, how many with four, how many with five. And then it says that there's 6 non-isomorphic trees. So 6 different trees with 6 nodes that look different. And the idea is to draw all of them. Now this is normally a collaborative task. So what we'll do is maybe I'll just do the first 3 numbers, and you can, if you want to pause it, do 4 and 5, something like that. Okay, so I'm going to use this paper here to do this. So let's see, so T of 1. So T of 1 is supposed to be the number of trees with one node. And well, there's only one. That's it. There's nothing else you can do. You can't draw any edges. Number of trees with 2 nodes. I think there's also only one, because you draw the 2 nodes and there's always one less edges. You have to combine the edges. So there's one. Number of trees with 3 nodes. Okay, I can think of a line. That's one of them. And is there any more? Okay, so how do we do this? Well, are there any more? And I can draw different shapes, but they might look different, but they're going to be the same. So I think if you think of adding an extra node to this, either it's connected to this, and they look the same. So there's only one way of doing it. Okay, so that kind of giving a hint for T of 4 and T of 5. To form a tree with 4 nodes, you take this and add on an extra node. I think that's all you can do. So if you want to pause it and try and find how many trees with 4 nodes, how many with 5, and then draw the 6 trees with 6 nodes. Now I've only got about 5 minutes left, so off I go. So pause me and try it. Okay. If you haven't paused me, here we go. Okay, so 4. I think the only options here are you can add the node here or here. If you add it here, it's the same as this one. So I think there's 2. So you get the line 1, 2, 3, and another line 1, 2, 3, and then you can either add it on here or here. Now, what will be a good exercise, actually, I'm very likely to make a mistake on this for you to see, can you find a mistake? So where can we add things here? So this essentially is a line. See, it doesn't look like a line, but if you just move it, it is. So I think there's 2 options here. You can either put it on one of these or one of the end ones, and they look the same. So either there or there. So that's building on this one. Sorry about the baby. Okay, so that's 2. Now what about this? So this thing looks like kind of a star to me. I can add on here, I think. I better just draw this, set it up. 2, 3. So I can join here or here. I don't think there's any other possibilities. And we have to be careful that we don't get something we've seen before. So this is where I think the possibilities lie. Yeah, you might find something that I didn't, which is fine. Now, I think you see we have this one already. Is this one genuinely new? So I'll throw this one out. Is this one genuinely new? We'd probably analyze by looking at the degrees. So all these have degree 2. Now, could these be the same? Yeah, these are the same as well, aren't they? Yes, I'm in a world of pain now because I'm actually not getting different things. So if I just move that over there, these two are the same. So I think there's possibly only 2 there, and I'm not sure is that right. And I'm going to be under pressure, especially with the time. I might have to go back to that. Can I draw 6? I think there's going to be more here. Oh, I don't know. This is something you can Google, I suppose. It's not examinable, so this is just a learning task for us to know what a tree is, that it has no cycles. Okay, can I come up with 6 non-isomorphic trees in 2 minutes? If I run out of time, it's up to you to kind of go off and Google it if you're really interested. Okay, that's one. How about I introduce one with a node of degree 3? 1, 2, 3. That uses 4 nodes. I don't know, have we got, yeah, we have one of them there. And I can go add on to this. That gives me another one, and I think I can do the same. Well, this is only 5 nodes, so I need to add on something else. 6. Now I need to get something different to that. I'm hoping that if I add the 2 on here in a row, that I can do that. So these are different because here there's 1, 2, 3 nodes of degree 1. No, yeah, and here there's, okay, here there's 2 nodes of degree 2, and here there's 2. Are these the same? Oh, this is tricky. I'm going to run out of time, definitely. So let's maybe look at the degrees. Degree 3, 1, 2, 1, 1, 2. And this one is 3, 2, 2, 1, 1, 1. So 3, 2, 2, 1. Yeah, you don't have that pattern, so these have to be different. 30 seconds left. How about we do degree 4? 1, 2, 3, 4. That's definitely new. And then I just have to add on something. Yeah, and then I can make a degree 5, I think. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. And that's different again. So the problem for you is to find the proper number of non-isomorphic trees of degree with 5 nodes. Okay, that was a struggle.